All right, hi folks. This is going to be a mechanism problem that we're going to discuss, and I would put this in the general context of ketones, especially when we start talking about alpha-beta unsaturated ketones. And this is what I would classify as a more advanced mechanism for an average organic 1, organic 2 corpse. Whenever looking at a mechanism, some of the first things I try to do is identify what bonds are being made or broken. And I do that by comparing the starting material to the product. And so one thing that I notice is that this double bond here is not present in the product. And so at some point, we're going to need to be able to do an addition to that double bond. And what I'll notice then is that this carbon-oxygen bond is the one that is being made or broken at the beta position to a carbonyl. And so remember that this is alpha and this is the beta site. And that these sorts of conjugate additions, or in this case, I guess it would be an oxo-Michael addition, is quite a common mechanism. The next thing I want to do is look at the rest of my molecule, and I often find it helpful to number the atoms from where I'm starting. So if I start there, I can go 1, 2, 3, 4, 5, 6. And that's actually a really big help in this problem because it lets me identify this carbon as being this carbon in the starting material. And so if I can identify that, then I can recognize that this carbon in the product is technically an acetal functional group. So it's one carbon bound to 2 different oxygen atoms. And so there's no net oxidation or reduction compared to the starting material as you go to the product. We're just taking that aldehyde functional group and we're incorporating it into the molecule in a different way. And so that also tells us then that this oxygen here that's 4 atoms away remains unaffected by the reaction. It's going to stay there. Okay, so that lets me map my product onto the starting material and identify some of the important bonds that need to be made or broken. And in this case, we've identified 3 really important ones. So the carbon-oxygen bond here at the beta position, and that's going to lead to the breaking of a carbon-carbon double bond, the formation of a carbon-oxygen bond, and we need to form this next carbon-oxygen bond here to incorporate that into the product as well. So with that outlined, typically the next thing I'll do is I'll look at what kind of reagent I have. And for those of you that are new to following us, I often try to label things as being either acids, bases, nucleophiles, or electrophiles. Those are your most common forms of reagents. And we'll also throw in there that sometimes we have oxidants or reductants as well. In this particular case, DBU is an amine base. It's typically classified as a non-nucleophilic strong base. And so we can use the general formula NR3 for that. Or if you prefer, we can simply use B lone pair for our mechanism. Okay, so with that, what I'm going to do is pause here for a couple of seconds and encourage you to click the pause button on this video and actually spend some time working through this on your own to see if you can complete the mechanism. Again, it's very important that you actually do that and spend a couple of minutes struggling through the details of the problem as your own opportunity to learn instead of just listening me go to the solution. So go ahead, click the pause button right now. All right, hopefully you actually took a minute or 2 there to try to solve this problem. And then what I'll do is go ahead and complete it here. And so one thing that's very important about identifying our reagent as being a base is that bases tend to deprotonate things. And so if we know that, then we can go look for acidic hydrogens in our starting material. And in this case, this OH is going to be a fantastic candidate for that. So we're going to deprotonate the OH. And I always like to try to balance my formula here. And so that means that we have an ammonium salt as the leaving group, is our BH+. And I'll also remind you that every time in an arrow pushing mechanism that you create a charged species, you want to make sure that that charge is balanced somewhere. And so if you're going to introduce a positive charge in the ammonium salt, then we want to balance that out with a negative charge, and that'll be on our alkoxide. Okay, and so here we go. That would be our alkoxide then to balance the charge out. Now we've gone from something that was a base, and of course O minus can be a base, but it can also be a strong nucleophile. And one thing that's really handy about recognizing these particular functional groups is now this is going to be a nucleophile, and our aldehyde out here is a really great electrophile. And so we're going to go ahead and have that O minus then attack the carbonyl oxygen. And when we do that, the bond that we've generated is this one right here. And so you can go ahead and add numbers again to the whole sequence, but we've now connected that O minus to the carbonyl oxygen. Okay, this O minus, just like the original O minus that we had over here, is now another nucleophile. And it's also, by the way, another base. So in many cases, the base can be a base or it can be a nucleophile. In this case, it could be either, but we now have an electrophile dangling out over on this alpha beta unsaturated carbonyl. And so we're going to use the new O minus that we formed to go ahead and attack at that position. So there we go. And this now would be an enolate. And so every time you make a intermediate that is a common intermediate in a number of these reactions, I encourage you to label it all on your own. The reason to do that is because the more you recognize and are able to name those intermediates, the more comfortable you'll be with them. And also, if you draw something that you're unsure of or that's new to you, it'll bring an alarm that it's something that's worth learning or checking on. Okay, and of course, enolates now can be either nucleophiles or bases. And if we scroll up, what we're going to do now to make the product is we're going to go back to our ammonium salt, which now is a weak acid, and we're going to have the enolate deprotonate that. And that will generate our base back. And so in principle, this reaction should be catalytic in base. And we will then get our product out. Okay, and so that's the mechanism. If I had to describe this in terms, what I would say is that we have a deprotonation event up here to form our nucleophilic alkoxide. That alkoxide then engages in an oxo-Michael addition or conjugate addition to the alpha-beta unsaturated ketone. That then generates an enolate intermediate, which behaves as a base and deprotonates this now weak acid that we generated way back at the beginning to generate our product and give us the base back. So I think that that's a good way to sum up the mechanism for this particular problem. One question that I've been asked in the past when I've put this problem up is that in the starting material, you know, there's more than one potential acidic spot. And often what I find is that students want to engage the aldehyde instead of the alkoxide. And so let me just draw that out here. And so this would be an aldehyde intermediate. There is an acidic spot here, and so our base could, in principle, deprotonate this to make the enolate of the aldehyde. And then this enolate could, in principle, do things. And of course, this enolate, just like the enolate up above, is a nucleophile and a base as well. And so in principle, it could attack another molecule of starting material. It could attack in a conjugate manner into the alpha beta unsaturated ketone, and that would be a Michael addition. And it could do a number of other things. The thing that probably drives this reaction in the forward direction has a lot to do with pKa's. And so I would encourage us to review that. So in this case, our DBU salt should have an aqueous pKa of about 14. The ROH, and in this case, it's a tertiary alcohol, so something like this. So maybe instead of just being ROH, we could look up tert-butanol as a specific example. This going to tert-butoxide plus H plus should have a pKa of about 18. And then that should actually be very close to the pKa of an aldehyde at the alpha position. And so because all of these pKs are very close together, proton transfers tend to be very fast. And so the proton can go on or come off and go on and go off. And all of those possibilities can coexist in the same reaction class. And really what drives this is the speed at which you form that initial 5-membered ring. And intramolecular reactions, particularly those forming 5-membered rings, tend to be very fast. And then after the first ring forms, it's set up really nice to do that second ring form reaction. And so if you tried to engage the aldehyde at this alpha position initially, that's an okay thing to consider. It's chemically sensible with this sort of base. And because this tertiary alcohol and the alpha aldehyde have very similar pKa's, it's something really worth considering. But I don't think that there's a good way to draw the arrow pushing mechanism to form this particular product engaging this kind of enolate. All right, so that's it for this question. Again, please go ahead and follow us. We really do appreciate the followers. And if you'd like to download this PDF, remember that you can follow us on Patreon as well as other social media accounts. So please do give us a like and please do subscribe and feel free to leave any comments in the video. Thank you for your time and have a good day.